Today I'm going to be talking to you about how to use the GSAS-EXPGUI software suite for analyzing your X-ray diffraction patterns. This is for analyzing powder X-ray diffraction patterns rather than looking at single crystal data. So the first thing that you do when you use GSAS-EXPGUI is you first open GSAS, and you just have to create a generic file that then you can then visualize in EXPGUI. So GSAS is kind of like the older version that you can do stuff in DOS, and you can just type lots of information into that. But to actually visually see what's going on, EXPGUI is what you use. But you need to set up an experiment using GSAS. So you do that by pressing Setup, Experiment Name. You give this file an arbitrary name, and our first example we'll be looking at is anatase, titanium dioxide, so I'll just call it anatase. Yes, so we'll create that file. And I think I made it on the desktop here, so I hope I'm not sure where it was. Then you have to press Setup, Expedit, so Experiment Edit. Okay, and then it says, do you want to create this file on your desktop? Yes. What will we call it? Anatase. Oh, now it's appearing. Do I want to do anything else? So it gives you a whole list of options of what you can actually do within the GSAS software. But I don't like DOS format. I like to see what's going on. I like a user interface. So I'll just press X for now and exit it. So I've just basically created myself a nice blank file here. I can't. That's nothing's been entered yet. Now I've got some examples in EXPGUI that I've already got set up. Okay, so here are the examples. And first we're going to look at an anatase powder, and we're going to do a Rietveld refinement for that. Now I know how to do Rietveld refinement and LAUR refinements. Okay, so if your powder there's no thermodynamic effects on which crystal planes it grows. So it grows into what is in the literature. You know, the different peak heights are what a literature powder pattern would have. So basically there was no strain on in which it was growing. It would just grow to where it's thermodynamically optimum state in different crystal planes, different orientations. So the Rietveld model is great for that. Okay. But then if you want to do a LAUR refinement, where you just relax that structure factor, that's you know, constraining that model. So you can use a LAUR refined model if you have preferred orientation effects. And I'll teach you how to deal with that as well. So for now we'll just model a powder which grows very similar to what you see in the literature in terms of its preferred orientation. So we'll just use the EXPGUI software now, and it will ask you, okay, open up this file. So I've created this blank file here, anatase experiment. I'm just going to move it to the powder here, delete this blank that I made earlier. So in EXPGUI I can go to these G6 examples, anatase powder Rietveld, and I can then open this experiment. And this is the user interface. Okay, so I'm going to teach you how to do a Rietveld model and a LAUR equally weighted model. So the first thing you want to do is enter what phase you're trying to model. So before you even go into this software and you're thinking, oh, I'm going to model my pattern, you should first use the correct software to identify what phases are present. So once you identify what it is, and for this particular example it's anatase, you can then add that phase here. So what phase, where do I get this phase from? Well, you can get it online from the crystal structure database, CSD. So if you're going to be modeling patterns quite regularly, what I recommend you do is you become a member of the ICSD. Using the ICSD is you can just search for that particular material that you know it is. Okay, so then I I know the chemistry of this material called anatase. That's the mineral of the material called anatase. Okay, and then it will give you, all of the standards that have been uploaded to the system. And what I like to do is I'd like to click on this filter and just take high quality crystal data only. And then you can click on any of these that are of interest to you, say this one, and show a detailed view of it. And it will give you the paper in which it was published, the title of that publication, where it was published, I think is somewhere as well. Can't see it. Oh, here it is. So then you have a reference, and it will give you some structural parameters and information. It will also give you a pattern of how it looks, and you can configure that pattern. You can tell it to display the indices, so then you can know, oh, okay, that's the 101 plane, 103, 004, 112, etc. And you can even change it, so you can change the minimum and maximum values that you want to change this range here. For instance, from 10 to 20 degrees 2 theta, there's no information, so you might just want to go from 20 onwards. And then you can extract that by pressing export XY data. Okay? So you also need to know, when you're doing your X-ray diffraction, you need to know what was your X-ray source. So here, to get this standard, as a sort of a starting point for the model, you have to export a CIF file. So export that CIF, and using that CIF, I've already put it here. So it's the same thing here. So this will be kind of like my starting point of what I'm trying. I'm going to take this starting point and actually make it reach what I've got. Okay. So in this phase section, you add the phase. I've got a CIF file, and I'm going to upload this CIF file. Press continue. Just say okay, yeah. Put all of those things in, thank you. And now this is the first phase that we're going to, it's a starting point, and we're going to refine that starting point to match our actual data that we got. But I haven't even uploaded my data yet. That's the next thing I have to do. So under the histogram tab, you go to histogram, you click on add new histogram, and then you select your data file. But it has to be in the correct format, which I haven't shown you how to do. So if you have your data and it's simply like this, so you have degrees 2 theta on the left and counts on the right, that's something that's handy, a handy way of having your data. Then you can convert that into a GSAS format. Okay, so using this called convex.exe tool, you can do that. And so the file type that I've got is just a simple ASCII, and I want to convert that to a GSAS. Okay, so I select the file that I want to convert. So that is, where is that? It's under C drive. Thought it was here. Okay, there it is. It was looking for a .dat file, DAT, but it was a .txt file, so it didn't see that. But they're both equivalent, I think, for the software, so it's fine. Now do that convert thing. And then here I get this is that ASCII file, but just in a GSAS format that likes to see the data of your X-ray pattern. So now within the software I can load, as I said before, go to histogram, add new histogram. I can load this histogram here by looking for that GSAS file, and pressing open. We like it it is a GSAS format, I know it's fine. Then you have to just select bank. Then you have to put an instrument parameter file. So this is something that whoever's in charge of that machine, they'll have an instrument parameter file for that specific XRD machine. and within that instrument parameter file it will have information, as I told you before, about is it copper as my source of X-rays, and other information that's vital for this software. I've already got that information here. It's called Phillips.ins. It's a bit old, but it works. So I'll just add that, and then press add, and everything's done now. Now, if I ever want to see what's going on, I press the live plot button, but I can't see anything yet because I haven't told it. Any changes that I've made, I haven't told the software, okay, make those changes. And to do that, don't know what the hell these buttons mean, but you have to press PowerPref and then genres. So all of the stuff I've just done, so adding the phase, adding my, so that's a phase in which we're going to starting point, and then adding my actual X-ray data. Now I can actually see it on the live plot. So these X's are my data. The green line is just the background that is drawn for me, and the red is the model. So as you can see, the model is kind of in the right place, but the heights aren't right. Okay, so that's something that needs to be refined. I'm guessing also the width won't be correct. So you can see the position is slightly out. There are many things that we need to start to refine to get this to work. But I think first thing first is just to check that the background's okay. And if I zoom in, I can see that my background pretty much goes through my noise. There's no point in really editing it in this case, but there are cases where you have like a broad background because the amorphous glass substrate is giving you something. There could be other reasons. So then you have to draw a background through that. And you can do that by clicking add and so forth, but I'll show you how to do that later for an actual scenario where it's important to do it. Now, let's actually start modeling, or we'll soon start modeling things. One thing that's important is the profile. Now, a lot of you guys are dealing with thin films, and this peak cutoff is just simply not wide enough to deal with the widths of the peaks that you get, because we're dealing with quite nanocrystalline materials quite often. So we need to change this peak cutoff. We need to add a couple of zeros. Okay? And there's something called damping. Now, the higher my damping value, the shorter the steps the software will take in finding the local minimum. Okay, when it's trying to fit a model to your data. Okay? So it's always advisable to start with a high number and move slowly towards that local minimum rather than going huge steps, because you can really mess things up. So I just like the number 7, I think it's quite lucky. So I've done that for phase as well, cell damping. So I think we're ready to start modeling things. So we're going to do a Rietveld model. It's already stuck on the Rietveld model here. And each cycle will do 7 cycles of modeling. So I'm going to start modeling the phase and nothing else. So I'm just going to move the positions of the peaks. So one thing here is called scaling. So if you remember, the heights of my model were not close to matching the heights of my actual data. This is ticked on, so it's going to move the heights, the peak heights, to the correct place. I don't change the damping here. That's not a big problem. So now to start modeling it, I press PowerPref and then genres. And that's modeling it. And here my reduced chi-squared is 32, so it's obviously not great. There are some issues that we're going to have to fix. Again, it's just not getting there. I think maybe we need to keep it going. So we'll press genres again. And we'll just keep pressing until it's refined that. We can see that slowly my chi-squared is going down. Now it's 17. And let's have a look at the live plot and see how we're doing. So we're getting much closer. It was just the scale factor was a problem. So I'm just going to keep going. So I'm going to increase this number. just so we can get the scale factor in the correct place. Well, it's not really changing much now. There are other things that I need to change. Now, in terms of the profile is things that change the width and asymmetry of your peaks. It can also shift your peaks as well. So the main three things that I use that I think are really important, are really handy ones, are LX, LY, and shift. Now LX, it's to do with the average crystallite of your material, the average crystallite size. So that's probably one of the first things that you want to model. But it just depends. So shift, sometimes you need to shift your 2 theta data because you didn't align your sample very well. Okay? So when you do an X-ray diffraction pattern, you need to make sure that the height of the sample is in the correct place. In this case, I'll be starting with just modeling LX. Now, whenever you check or uncheck a box in Rietveld mode, you always have to press PowerPref first, and then joiners again before you start modeling things. And now my chi-squared is down to 12. It means things are getting quite good. And as you can see, it is getting quite good. It's getting quite close. I just need to continue refining and hopefully we'll get there. Okay. So right now I currently have my refined cell. So it's changing A and C, because A is equivalent to B. It's changing A and C of my unit cell, the width of my unit cell and length. And right now it's currently changing the average crystallite size. So it's doing all of these things to try and match my pattern. But as we can see, it's not really changing much now. And it's not quite reaching the width that is predicted. I think perhaps there's a problem with the pattern, with the way it's trying to model these points too much down here rather than the points up here. So maybe I have to change this manually because it's not doing a very good job. So right now it's 4. Yeah, that number is 4. So I'm just going to change it manually to say 2 and not model it and see if that helps things along. That's made things worse. Oh, that's a bit weird, isn't it? Shouldn't be doing that. I think the issue is that this peak is quite wide, whereas it matches quite well with the other peaks. So I should leave it as it is and let it just refine that. But I'll change the damping a bit so it can go in bigger steps. So it is modelling quite well. On average, all of the peaks are being modelled quite well. And I think that's the best it's going to get for that peak, but for the rest of these peaks it's doing quite a good job. Ish. So there are other sort of fudgy things that you can do to try and improve that. So let's just try and changing the strain. Perhaps the strain is causing an issue, I doubt it. It's not strain. Maybe there's a slight error in the measurements, it needs to be shifted. Again, that's not the issue. Now we come to these parameters, GU, GV and GW. Now this just changes the Gaussian shape of your material to try and make it match. But I prefer to deal with LX first before I deal with anything else, because this is actually a number that you can then relate to crystallite size, and these numbers you can't really relate to crystallite size, so it's best not to fudge with these first. It's best to fudge about these things afterwards. Okay? So let's start with GU and see if we can improve things. And that's made things not better at all. I just have a feeling that it's not going to get any better. It's not bad, but it's not great either. But for this example, I hope you understand how then we've got the lattice parameters now, and again from the profile we've got Lx, which can be related to the average crystallite size of your material using this equation here. So normally we take, from the Schur equation, normally we take k as some arbitrary number around 0.9 is often what is used, and x here will be your Lx number, and this will give you the average crystallite size in angstroms. Okay, so don't forget to convert it to nanometers, which is the convention in our field as materials scientists. So I think that example is pretty much done, but one thing that you can do is if you press results list view, it lists some really important things that we've just modelled. For instance, chi-squared, so that's the measurement of how good our fit is. But generally, what people like as crystallographers is the WRP value. And if this WRP value is low, so 0.58, I don't think is that great. We didn't get it to fit very well to the model. And also you can then, if you scroll down, you've got your A, B and C, that's my unit cell parameters of my tetragonal anatase unit cell, and this is the error associated with each value is quoted below. So that's also interesting to have. Okay. So we'll move on to the next example. So the next example we have is a phase mixture. So we have an anatase rutile powder phase mixture. Let's have to give it a blank experiment file. I'll just call it anatase rutile mixture. And I'll open it here. So again, I'll add the phases. So from the database, I've already got my anatase and rutile files. I'll add those. So my first phase is anatase. My second phase I'm adding is rutile. Then I want to add my histogram, which I might need to convert using convex. Yep. Put my instrument parameter file, press add, and then press power pref and draw on this so it can register those changes, those additions I've just made, and see it on the live plot. Now this time you can see we have more peaks. So this is the peak that we saw earlier. This is the anatase 101 peak, and now this is the rutile 110 peak. So we'll be modelling both phases together. So if we can see the background, it's a pretty flat background, so I don't need to modify that at all, so it's quite fine. So what I'll do is, again, I'll dampen my cells. Change my peak cutoffs, make it slightly wider. And then I'll start to model things. First thing I'll do is I'll just model the phases. The anatase, number 1 phase, rutile, number 2 phase. Remember, in Rietveld mode, you check things, press power pref first, then genres afterwards. In the bell mode, it's different. Now I'll just let it refine for a while, 17 cycles, and at my chi-squared value, it's not going down a huge deal. Now we're starting to get better. I'll refine again. It's not getting much better. And let's take a look at how that model is fitting my data. It's not doing a great job, okay? And that's because I haven't modeled the phase fractions. Okay? So under scaling, you can tell these phase fractions, okay, start to let it go to what is the true phase fraction now, because it starts off with a number 1 and 1. That doesn't necessarily mean 50-50, okay? Because your different phases have different densities and they diffract X-rays slightly differently. So you have the software takes this all into account. So 1-1 here does not necessarily mean 50-50. I'll tell you how to get the real phase fractions out afterwards. But for now, we'll refine those. Power pref and genres for 7 cycles. We'll do that again. It's doing okay, it's just not going to the right peak heights. I think I need to start modeling the widths of my peaks. So now on the profile, again I'll start with my LX, which is related to my average crystallite size. I'm refining that. It doesn't see, oh, it's gone a bit weird. That's fine now. For some reason it's going very strange at the end. What's going wrong? I guess I have too many things checked. So I'll just put some arbitrary numbers here and try and figure out what's going wrong. It's a good thing when things go wrong in the sense that you can then learn how to fix them as I'm here. Okay, that's working fine. Now what I'll do is I'll just turn the scaling off and the lattice parameters off, but then now refine the average crystallite size. Because sometimes in your model, if you have too many variables, it's not a good thing. It seems to behave itself a bit better now. And again, it's not perfect, but it's quite close. Okay? So that's not bad. And again, you can go through many iterations of trying to improve the average crystallite size, or if there's an error in your shift because you think the sample's misaligned, or if there's any strain. Things like this you can play around with, go through many iterations until you reach the optimum. The one thing that I think is pretty interesting using the live plot, if you're not familiar with where the peaks are, you can look at tick marks. So if you press tick marks, phase 1, it shows you where all of the peaks are for the anatase phase. If you press tick marks, phase 2, it shows you all of the peaks where the rutile phase is. Okay? So here, 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 etc. And one thing, once you're done modeling your pattern, if you want to have all of this information in a way that you can then publish it, you can press File, Export Plot as a CSV file, and then you can open this CSV file in Excel. Okay. So then you have the data and you can play about with it however you want. Okay? So now in terms of getting the phase fractions, what we can do is we can again press results list view, and it tells you the WRP, which is the measure of the error. So it's too wide. Your chi-squared again is another measure of the error. For your histogram, it gives you information about okay. Oh, because we weren't modeling the lattice parameters in the last cycle, it doesn't show us the lattice parameters. So what I'll do is I'll turn these things off, turn these things back on. Check that everything's okay. It's fine. Now I can press results, this view, and then once we scroll down, okay, here it is. Phase 1, this is my A, B and C, my lattice parameters, the errors. Phase 2, the lattice parameters and errors. And I think, okay, here we are. So phase element fractions for phase number 1, weight fraction is 0.42, and weight fraction is 0.57 for phase number 2. So it's from these weight fractions that then you get your composition. Okay. Now I'm dealing with the same phase, chemical composition. Is that there are two different polymorphs of TiO2. So if 0.42 weight fraction is anatase and 0.57 weight fraction is rutile, then that is actually my composition. It's 43% anatase and 57% rutile, because both are different polymorphs of titanium dioxide. But if you have two different materials, then the weight fractions won't necessarily be the atomic fractions. So you need to account for that. Okay, and that's that example done. So the next example I want to look at is looking at a thin film rather than a powder. So again, using the software EXPGUI, we open that, go to that, and because it's a thin film, we have preferred orientation. You don't always get preferred orientation effects with thin films, but you very often do. So same routine. Remember, whenever you have an X-ray pattern, you have to identify which phases are there. I've already done this. It's just anatase. So I'm uploading a good starting point, an anatase from the literature CIF file. I've shown you how to do that earlier. I'm going to add my histogram, which I've already converted to GSAS before. Okie doke, so I want it to register what I've just done. And then I'll look at the live plot. So this is the sort of bumpy background I was telling you about before. It's broad, and I know this feature because I see it often. This is just due to the amorphous silica glass that's underneath the substrate. So to get rid of that, rather than try and model it, it's mainly amorphous, you don't really want to care to model it. You just have to edit the background. So what you do is you zoom in and you click here and there where you think that background should be. And the more time and care that you take with it, the better. Now sometimes with certain machines you get little bumps at certain values of 2 theta because there's an error of the detector or something like that. So you need to be aware where the artifacts are in that spectrometer, if that's the case, if there's a problem with that spectrometer, and model the background accordingly, or draw the background accordingly. And sometimes at the edges the background goes a bit weird, so you just have to add a few more points, but then not add any more terms, and it does a better job. Okay. Now we press paragraph joiners, and it should register what I've just done, those changes. And now I can see that the background goes much better through the data. The one thing I can notice straight away, so if I just look at the relative heights of my peaks, this peak here, the 112 peak in anatase, it doesn't show the same distribution as it did before. So I know there's preferred orientation in that respect, and over here I think this is the 211 or 112 peak of anatase. There's a problem there as well. So I know there's preferred orientation. So if I try and fit things to a Rietveld model, it's just not going to work. It'll only work if I use a Rietveld plus a March-Dulles or spherical harmonic preferred orientation model added on top. Okay? But if you don't care to do that, if you don't care to quantify your preferred orientation in some respect, if you don't care to quantify it, then you can just relax those preferred orientation effects using the LAUR method. And I'll show you how to do that. But first things first, let's change my peak cutoff, make it wider, and change my dampings accordingly. And now I'm ready to do my LAUR method. Now, with LAUR method, you have to have everything unchecked when you press PowerPref. The only thing that you can have checked is the scaling. Nothing else can be checked. And with the LAUR method, you have to press PowerPref once, and then joiners twice. I don't know why, you just do. Okay? Now I can start to check things. So I want to start to refine my phase. I'll do it a couple of times. Now look at my material. If you remember before, the peak heights were quite different. It was, the distribution was, the middle was the highest and the two on the edges were the same height. But you see it's starting to relax that structure factor and allow things just to fit in any thermodynamic direction. Okay? So we just need to continue to press joiners, try and reach the local minimum. I can now start to model the crystallite width. It's doing a much better job now. My chi-squared is down to 1.8. It's not going to get much better than that. And we're almost there, I'd say. And you just need to go and do more and more iterations to try and get things to match more perfectly. But as you can see, there's some slight asymmetry. Perhaps, potentially, there's some rutile impurity there, or it could just be noise. So, you know, you can then model the asymmetry, the strain. So once you model the strain, you can then quantify the strain using this equation here, where rather than just using y minus yi, you just put the ly value there. So we can model those things, or perhaps, you know, the beam wasn't perfectly aligned. So let's just go through each one in turn and try and see if things improve or if they don't. So there wasn't much strain. the beam was probably well aligned. And there's not a huge amount of asymmetry. You just go through those iterations and it slowly will get better. Okay. Another thing you can do is you can model your baseline. Okay. You can tell it to relax a bit and move so that peaks can fit better. And that's advisable because I've drawn a line by eye. I don't know what exactly is the contribution from the amorphous silica background. So it's advisable to put a very high damping factor and to refine your background very slowly. I'll do that whilst refining my phase and my crystallite size. .802, 1.795. It's getting slowly better, but now it's got worse. That's 1.8, and that's where you call it a day for refining the background. It's just not going to get better. But as you can see, it's moved the background a little bit, shifted it to allow it to try and improve things. What you can sometimes do as well is, for your histogram, because there's no data here, there's no point in trying to improve things. So you can set data limits and exclude regions. Okay, so you can see if that actually worked. I don't know if it worked. Oh, it has worked. Okay. Oh, it's fine. We'll get everything back. So now we start to model things again. So we'll have to edit this background. Power John is twice, remember, we're in LAUR mode. And now we can start to just try and improve things again. Just increase the number here, so look at the live plot, see how it's doing, and then I can try and refine that background again to make things better. But I'd say that's pretty damn good. I mean, for a thin film, it's not bad at all. So then, again, as before, you can go to list view, get your errors out to 0.18, that's respectable, and you can then extract the lattice parameters. And that's pretty much all you can get from this information, from what we've done. One thing you can do, if you care to quantify, the texturing, they call it, the preferred orientation, you can go to results, ref list. We want to look at histogram 1 and press S for all of the data. And you just press enter, etc. Now this data here, it will give you the copper K alpha 1 and copper K alpha 2 contributions. So for the 101 peak, from K alpha 1 and K alpha 2 contributions, we've got a contribution of 14.5 and 6.7. For the 103, we've got the 1.05 and 6.687. So you can take these numbers, add them, and that will give you the relative intensities of each peak. Okay, and then you can quantify it relative to each other or relative to changes versus a single crystal. Okay, and that's that example done. Now we're going to look at the exact same film again, but this time rather than doing it in LAUR mode, we're going to do it in Rietveld mode, and we're going to use the spherical harmonic model, which I do not claim to be any kind of expert at using, but it's a way of quantifying or semi-quantifying the amount of preferred orientation you have. So again, I'm just going through the motions now. I have to add the phase. You guys are probably getting bored of this, but practice makes perfect. I'm going to add our histogram. And I can't stress that anymore. I mean, to use this software, practice is essential. Otherwise you'll forget how to do these little things. And you might find much better ways of doing it than I do. Probably will. So, read the manual and explore things. So the manual is available online if you just type in GSAS manual. But it's quite detailed and quite in depth, and you wouldn't get the kind of information, the basic way of doing things that I'm telling you. But if you want to look for specific things, you can look here under the in the index section. Okay, so this spherical harmonic thing that I'm about to tell you is spoken about in the GSAS technical manual, and they refer to a paper here, which, if you're going to use that spherical harmonic model, you should reference this paper and read it and try and get a grasp of what it truly means. Now I'm just going to fit my background as I did before. Well, what I think I'll do first is delete the background. So just going to exclude this data here. See if it's worked. It seems to have worked just fine. Now I'm going to start to model things first, and then I'm going to show you how to use the spherical harmonic model. Now there is the March-Dulles model as well, but I don't like it because it's only good if you know for a fact which plane your material is growing. So sometimes if you have epitaxial growth, I'm not sure many of us deal with epitaxial growth. So we're doing sort of chemical depositions where it gives it that flexibility to grow in many different directions. But whereas in other materials growth, for instance physical vapor depositions, where you're growing on a lattice-matched substrate, you often get growth in one particular direction, and the March-Dulles function is very good. So if you know that it's growing, say, just in the 101 direction, you can specify 101 and give it that ratio here to grow or not grow in that particular plane, and the other planes will obviously go down in growth subsequently. But what I found with films, the thin films I've made, is that once you enter one plane, it doesn't often work for one plane, and you enter 2 or 3 planes to make it work, and you're just creating whatever. I mean, you're opening Pandora's box because there's so many different possible combinations that could work. So rather than doing it manually, it's better to just let the spherical harmonic model do that for you in many different planes and try and get a quantitative analysis in many different planes. So I'm just modeling the lattice parameters and the crystallite width. It doesn't seem to want to get much better because of the problems with preferred orientation. Here you can see there's a big problem with preferred orientation. Okay. Also, my background sucks, so I need to fix that. So whenever I uncheck something, first I press power preference on this just so it registers that change. And then now I can fix my background, because that was a big problem as well for the model, because that background really doesn't fit.
But first, you still continue this way with Java. Refining the original one is the same or not?
It's similar, but I like to give it. I like to start off with what by eye looks good, and then let it move, because sometimes it just moves into a completely wrong place because it doesn't know what to do. So I like to give it a good starting point. So again, it's personal choice. I mean, you can just go ahead and press refine background without manually editing it and just see how that goes. It plays out for you. But I like to do it myself. So now I'm going to start working with the spherical harmonic. It's really easy to use. You just tell it the order. So I found that 6 or 8 works really well, but you can try whatever works for you. And the idea is to get the lowest order to work for you. Okay? But whatever you do, if you're analysing a series of samples, be consistent. So I'm going to go for 8. Sorry, 8. And it's going to try and push growth in these different axes. I'm going to give it a high damping. As you can see, my chi-square is going down. Things must be improving, and they are. And if you look at my spherical harmonic numbers, they've all changed. And it gives you something called a texture index. Now, how it gets that texture index, I'm not sure. I haven't read the paper. I need to. But it's something that we need to understand. But it gives us a semi-quantitative parameter of how textured your material is. So again, you just continue to refine the preferred orientation. I've unchecked it for now because I want to start to refine my background. Just a tad. I think that's enough for the back. Maybe just a little bit more. Make sure that 1.329. It's improving, but I mean steadily. And again, you just go through many iterations of this. Until you reach a true minimum. And that's not bad. I mean, that's very good actually. In terms of the blue is the measurement of the difference between your model and the data. And it's very flat, so that's great. That's a good fit. Okay. And this number here, I mean these numbers you can note them down. But this texture index is just going to give us a semi-quantitative parameter that we can then compare with another film that I've made. And that'll be the last example for today. So it's just basically going to be a repetition of what I've just done, but for another sample. And the difference between these samples is so simple. One sample I made by chemical vapor deposition using a set parameters, and my deposition time was 2 minutes. Now, the second material, I did exactly the same thing, but my deposition time was for 4 minutes. but there's a very big difference in the preferred orientation. And you'll see that very soon. See? Huge preferred orientation in this film. There's absolutely no growth in the 101 plane under these conditions for some strange reason. I don't know why, but that is the case. That was the case. So I'm just going to make sure everything's okay. Now I'm going to turn it on. I forgot to model my background, but it was pretty flat anyway. So I'm not sure if that's a problem. Let me just double check my background is okay. Okay. Because there was so much preferred orientation in this film, the model got really confused at first, but now I think it's finally found its way. And there we are. It's got an almost perfect fit as well. Don't forget that you can export this data by pressing File Export as CSV file. But there's massive preferred growth. I think this is the 211 plane. And if we look at the preferred orientation texture index, now it's 470. I mean, there's a huge difference in that texture index. So it had to really, really fudge things to make it work. So this texture index gives you an idea of the preferred orientation in your film. And that's how you do that.